Right now, the Milky Way is moving at nearly 600 kilometers per second toward a region of space we cannot observe directly. This motion is measurable, consistent across multiple sky surveys, and confirmed by the dipole pattern in the cosmic microwave background. The Great Attractor is not a theory. It is a gravitational influence strong enough to redirect the paths of entire galaxy clusters. Tonight, we will examine the data behind that motion: redshift catalogs, large-scale flow maps, radio and X-ray observations, and the mass concentrations hidden behind the Milky Way's dense disk. You are invited to follow each step calmly as we rebuild the evidence that points toward this structure. That measured motion becomes the starting point for Part 1. Why is the Milky Way racing at 600 kilometers per second toward something we cannot see? The most disturbing aspect of our galaxy is not its size or age, but the fact that it is not stationary. The Milky Way is currently moving through space at close to 600 kilometers per second, carrying every star, every planet, and every cloud of gas along with it. This motion is not inferred from theory or speculation. It is measured directly and confirmed through independent observations using entirely different methods. The earliest and most reliable reference for detecting this motion comes from the cosmic microwave background. This radiation, released when the universe was about 380,000 years old, forms a nearly uniform backdrop across the sky. When NASA's COBE satellite measured it in the late 1980s, scientists noticed a subtle but systematic temperature difference across opposite directions of the sky. One side appeared slightly warmer, the other slightly cooler. The simplest explanation was relative motion. Subsequent missions refined the picture. WMAP reduced uncertainty. ESA's Planck satellite confirmed both the direction and magnitude with much higher precision. Together, these datasets show that the Milky Way and the entire local group are moving relative to the cosmic background toward a region near the constellations Centaurus and Norma. This result has remained stable for decades. At first, astronomers attempted to explain the motion using nearby structures. The gravitational interaction with Andromeda contributes a small component. The pull of the Virgo cluster, located roughly 16 megaparsecs away, adds more. Yet when these contributions are combined, they still fail to account for the full velocity. The numbers do not balance. This mismatch forced astronomers to reconsider scale. If local structures were insufficient, the source of the motion had to be both more distant and far more massive. The problem was no longer about individual galaxies, but about coherent motion across large regions of space. During the 1970s and 1980s, astronomers began assembling large redshift surveys. These surveys measured not just where galaxies were, but how fast they were moving. Projects such as IRAS, followed later by 2DF and the Sloan Digital Sky Survey, revealed that many galaxies exhibited velocities that could not be explained by cosmic expansion alone. These deviations, known as peculiar velocities, showed a striking pattern. When plotted in 3 dimensions, the motions were not random. Entire groups of galaxies were drifting together. The flow lines converged toward a region of the sky that optical telescopes struggled to observe because it lay behind the dense plane of the Milky Way. This region became known as the zone of avoidance. To investigate further, astronomers turned to wavelengths capable of penetrating dust. Radio observations from facilities such as the Parkes Observatory revealed galaxies hidden from optical view. X-ray telescopes, including ROSAT and later Chandra, detected hot intra-cluster gas trapped by deep gravitational potentials. Infrared surveys from Spitzer and ESA missions filled in additional structure. Together, these observations pointed toward a massive concentration of matter centered near the Norma cluster, also catalogued as Abell 3627. This cluster contains thousands of galaxies and a vast amount of dark matter, making it one of the most massive nearby structures known. Surrounding it is a broader region of enhanced density, now commonly referred to as the Great Attractor region. Importantly, this is not a single object. It is an extended mass concentration spanning tens of megaparsecs. Its influence arises from accumulated mass rather than proximity. According to general relativity, mass curves space-time, and the combined curvature produced by this region is sufficient to redirect galaxy motions across enormous distances. Further confirmation came from velocity field reconstructions in the early 2000s. Using distance indicators such as the Tully-Fisher relation, astronomers built maps showing how galaxies move relative to the expansion of the universe. The Cosmic Flows projects revealed stream-like patterns in the local universe, with many paths converging toward the Great Attractor region before continuing beyond it. The Milky Way fits cleanly into this pattern. It is not moving independently. It is responding to the same gravitational landscape that shapes the motion of neighboring groups and clusters. This behavior is exactly what physics predicts when matter is distributed unevenly on large scales. Dark matter plays a central role. Observations show that visible galaxies and gas account for only a fraction of the inferred mass. Estimates based on galaxy dynamics and X-ray temperatures indicate that dark matter outweighs luminous matter by several times in this region. Although invisible, its gravitational influence is measurable and consistent. Independent evidence comes from bulk flow measurements, which track coherent motion over hundreds of millions of light-years. Different research teams, using different techniques, consistently recover similar directions and velocities. While uncertainties remain, the convergence of results strengthens confidence in the overall picture. The Great Attractor is therefore best understood as a feature within a continuous gravitational landscape. The Milky Way's motion reflects the combined pull of nearby clusters, intermediate mass concentrations, and even larger structures farther away. Among these influences, the Great Attractor represents a dominant local basin shaping our current trajectory. As surveys deepen and instruments improve, this picture continues to sharpen. Missions, such as JWST and Euclid, are refining our understanding of mass distribution in obscured regions. Each new dataset reinforces the same conclusion: the Milky Way is moving in response to gravity, not chance. And as astronomers traced these motions backward through decades of observation, a critical realization began to take form, one that explains how this strange behavior was first noticed at all. That realization opens directly into Part 2. How did astronomers first realize galaxies were moving the wrong way? The first sign that something was wrong did not appear as a dramatic discovery, but as a quiet inconsistency hidden in columns of numbers. By the middle of the 20th century, astronomers believed they understood how galaxies should move. According to Edwin Hubble's measurements, space itself was expanding, and distant galaxies were expected to recede from us at speeds proportional to their distance. This relationship worked remarkably well, and for a time, it gave the impression that the large-scale motion of the universe was simple, orderly, and fully accounted for. But as observational tools improved, the numbers stopped behaving as expected. In the 1960s and 1970s, astronomers began measuring galaxy distances with greater precision, using techniques such as the Tully-Fisher relation, which links a spiral galaxy's rotation speed to its intrinsic brightness. These distance estimates were paired with redshift measurements, allowing scientists to separate a galaxy's motion caused by cosmic expansion from any additional motion layered on top. What they found was unsettling. Many galaxies were moving faster or slower than the expansion alone could explain, and not in random directions. These extra motions became known as peculiar velocities. They were not peculiar in the sense of being rare, but peculiar because they did not fit the simple picture astronomers expected. In principle, small deviations were anticipated. Nearby galaxy clusters exert gravitational pulls on one another, and local interactions can slightly alter velocities. What surprised researchers was the scale and coherence of these deviations. By the late 1970s, teams led by astronomers such as Alan Dressler and Donald Lyndon Bell were compiling catalogues of galaxy motions across large regions of the sky. When they plotted the data, patterns emerged. Groups of galaxies separated by tens of millions of light-years appeared to share similar velocity offsets. They were not simply moving away from us with the expansion. They were drifting together in a preferred direction. At first, this was treated with caution. Astronomers are trained to distrust patterns that could arise from incomplete data or systematic error. Distance measurements were difficult, uncertainties were large, and selection effects could easily distort conclusions. But as independent surveys repeated the measurements, the same trends persisted. The development of infrared astronomy played a key role in clarifying the picture. The IRAS satellite, launched in 1983, conducted an all-sky infrared survey that revealed thousands of galaxies previously hidden by dust. When these galaxies were added to redshift catalogues, the flow patterns did not dissolve. They became clearer. The motions pointed toward a region of space that optical telescopes had long struggled to observe. This region lay behind the dense plain of the Milky Way, an area crowded with stars, gas, and dust. Astronomers called it the zone of avoidance because traditional surveys avoided it out of necessity. Yet gravity does not respect observational boundaries. If something massive lay there, its influence would be felt regardless of whether it could be seen. As redshift surveys expanded through the 1980s, astronomers began mapping thousands, then tens of thousands, of galaxies. Each new dataset added weight to the same conclusion. The peculiar velocities were not random noise. They formed a large-scale flow. Galaxies were moving as if responding to a gravitational pull from a direction partially concealed from view. One of the most important confirmations came from comparing these galaxy motions with the cosmic microwave background. The background radiation provides a natural reference frame for the universe as a whole. When scientists compared galaxy velocities to this frame, they found a consistent offset. The local group, and many neighboring galaxy groups, were moving together relative to the background. This agreement mattered. It meant the galaxy surveys and the background radiation were telling the same story using entirely different evidence. The universe was not expanding uniformly from our perspective. There was an added motion, superimposed on the expansion, shared by many galaxies across a vast region. As computing power improved, astronomers began reconstructing velocity fields rather than analyzing galaxies one by one. By treating galaxy motions as part of a continuous flow, they could visualize how matter was moving across space. These reconstructions revealed stream-like patterns converging toward the same obscured region. The idea of a gravitational attractor emerged naturally from the data. The name Great Attractor was not meant to imply a single object or a final explanation. It was a descriptive term, a way to label the source of the observed pull until its nature could be better understood. What mattered was not the name, but the realization that galaxy motions were tracing the distribution of mass on scales far larger than individual clusters. Throughout this period, skepticism remained healthy. Astronomers debated whether the flow could be explained by known structures such as the Virgo cluster or the Hydra Centaurus region. Careful modeling showed that while these structures contributed, they could not account for the full magnitude or direction of the observed velocities. Something more massive or more extended had to be involved. The turning point came as multi-wavelength observations converged. X-ray telescopes detected hot gas trapped in deep gravitational wells behind the Milky Way. Radio surveys revealed clusters of galaxies aligned with the inferred flow direction. Each method filled in a different piece of the puzzle, reducing the likelihood that the pattern was an artifact of measurement. What emerged was a new understanding of motion in the universe. Galaxies do not simply ride the expansion of space. They respond continuously to variations in mass density. Where matter is more concentrated, space-time curves more strongly, and galaxies adjust their trajectories accordingly. The peculiar velocities were not mistakes. They were signals. This realization changed how astronomers interpreted redshift data. Instead of treating deviations as errors to be averaged away, they began to see them as probes of unseen structure. By measuring how galaxies move differently from the expansion, researchers could infer where mass was hidden, even when light failed to reveal it. The story behind this shift is one of persistence and restraint. For decades, astronomers resisted drawing dramatic conclusions from incomplete maps. They refined distance indicators, cross-checked surveys, and waited for independent confirmation. The recognition of large-scale flow was not the result of a single paper or instrument, but of many cautious steps taken over many years. By the end of the 20th century, the evidence was difficult to ignore. Galaxy motions across hundreds of millions of light-years showed coordination. The expansion of the universe was real, but it was not the whole story. Beneath it lay a pattern shaped by gravity, tracing the invisible architecture of matter. NASA summarized this perspective succinctly in later analyses of large-scale structure, noting that galaxy velocities provide one of the most direct ways to map mass in the universe, including matter that does not emit light. ESA missions and ground-based surveys reinforced the same conclusion, each adding resolution and confidence. What began as an annoyance in the data became a tool. Peculiar velocities, once treated as errors, became guides pointing toward the deepest mass concentrations nearby. The realization that galaxies were moving the wrong way was, in fact, the realization that astronomers had been looking at the universe from too narrow a perspective. And as these velocity maps grew more complete, another complication surfaced. The region drawing galaxies inward did not appear to be the end of the flow. Beyond it, the data hinted at even larger structures exerting influence from still greater distances. That tension in the maps leads onward, opening into Part 3, Why is the Great Attractor hiding behind our own galaxy's glare? The most frustrating detail about the Great Attractor is not its distance or its mass, but its position. The region, exerting one of the strongest gravitational pulls on the Milky Way, lies almost directly behind the brightest, densest part of our own galaxy. From Earth, our line of sight toward this direction cuts straight through the Milky Way's disk, where stars crowd together, gas thickens, and interstellar dust absorbs and scatters visible light. For much of modern astronomy, this made the Great Attractor effectively invisible. Astronomers refer to this obscured region as the zone of avoidance. The name does not imply mystery by design, but a practical limitation. Optical telescopes, which collect visible light, struggle to see through the dense dust lanes that trace the Milky Way's spiral arms. Even nearby galaxies can vanish behind this foreground clutter. When astronomers first mapped the large-scale distribution of galaxies, the zone of avoidance appeared as a conspicuous gap, an empty band across the sky. That apparent emptiness was misleading. Gravity does not vanish where light is blocked. If a massive structure lay hidden there, its influence would still be felt through galaxy motions. This is precisely what puzzled astronomers in the late 20th century. The peculiar velocities, described in earlier surveys, pointed toward a region that appeared blank on optical maps. The mismatch between gravitational effect and visual evidence was not a contradiction in physics, but a limitation of human instruments. The first step toward resolving this problem came from expanding astronomy beyond visible light. Radio astronomy, which detects long-wavelength radiation unaffected by dust, offered a way forward. In the 1980s and 1990s, surveys conducted with instruments, such as the Parkes Radio Telescope in Australia, began detecting galaxies through their neutral hydrogen emission. These observations revealed a population of galaxies hidden behind the Milky Way's disk, filling in parts of the zone of avoidance. As radio maps grew more complete, they showed that the apparent gap in galaxy distribution was an illusion. Structures continued smoothly across the region, including clusters aligned with the direction of the inferred gravitational pull. This was an early indication that the Great Attractor was not a theoretical construct, but a real concentration of matter concealed by foreground dust. X-ray astronomy added another critical layer. Massive galaxy clusters contain vast reservoirs of hot gas heated to tens of millions of degrees. This gas emits strongly in X-rays, which can pass through dust that blocks visible light. Satellites such as ROSAT and later NASA's Chandra X-ray Observatory detected bright X-ray sources in the direction of the Great Attractor. These emissions traced deep gravitational wells, confirming the presence of massive clusters hidden from optical view. One of the most significant discoveries in this region was the Norma cluster, also catalogued as Abell 3627. Located roughly 65 million light-years away, it is one of the most massive clusters in the nearby universe. X-ray measurements showed hot gas confined by a gravitational potential consistent with a large dark matter halo. The Norma cluster sits near the center of what astronomers describe as the Great Attractor region, anchoring a broader network of mass. Infrared astronomy further sharpened the picture. Infrared light has shorter wavelengths than radio waves, but longer than visible light. allowing it to penetrate dust more effectively. Missions such as NASA's Spitzer Space Telescope and ESA's Infrared Space Observatory revealed galaxies whose starlight was heavily reddened by dust, but still detectable in infrared surveys. These observations expanded galaxy catalogues in the zone of avoidance by thousands of objects. Together, radio, X-ray, and infrared data transformed the zone of avoidance from a blank region into a partially mapped landscape. The Great Attractor was no longer hidden completely, but it was revealed in fragments, each wavelength offering a different piece of the structure. This multi-wavelength approach became essential because no single method could capture the full mass distribution on its own. The process of reconstruction required patience and restraint. Astronomers could not simply overlay images and declare a solution. Each dataset came with its own biases and limitations. Radio surveys were sensitive to gas-rich galaxies but could miss gas-poor ellipticals. X-ray observations highlighted massive clusters but not the surrounding filaments. Infrared surveys detected stars but provided limited information about dark matter. Only by combining all three could a coherent picture emerge. As computational methods improved, scientists began integrating these datasets into three-dimensional models. By combining galaxy positions with velocity information, they could infer how mass was distributed behind the Milky Way's glare. These reconstructions consistently showed a dense region aligned with the direction indicated by peculiar velocity flows. NASA described this approach as using galaxies as test particles, responding to gravitational forces that reveal the shape of invisible structures. Even when light failed to trace mass directly, motion provided the necessary clues. This principle lies at the heart of modern, large-scale cosmology. The challenge of observing through the Milky Way also shaped the design of later missions. ESA's Gaia mission, although focused on mapping stars within our galaxy, contributed indirectly by refining our understanding of the Milky Way's structure and dust distribution. By modeling the foreground more accurately, astronomers could better correct for its obscuring effects when studying distant objects. More recently, surveys using the Atacama Large Millimeter Array and other radio interferometers have continued to refine maps of hidden galaxies. These instruments provide higher resolution and sensitivity, revealing smaller structures embedded within the larger mass concentration. Each improvement narrows the uncertainty surrounding the Great Attractor's true extent and composition. Despite these advances, the Great Attractor remains difficult to define with sharp boundaries. It is not a single object with a clear edge, but a region where mass density rises above the cosmic average. This makes it fundamentally different from a galaxy or a cluster. It is better understood as part of the cosmic web, where filaments intersect and matter accumulates. The difficulty of observing it directly has had an unintended benefit. It forced astronomers to develop techniques that rely less on brightness and more on dynamics. By focusing on how galaxies move rather than how they look, scientists gained a deeper understanding of the universe's hidden structure. This shift has influenced studies far beyond the Great Attractor, including investigations of dark matter and cosmic flows on even larger scales. The history of the zone of avoidance is also a reminder of perspective. From Earth, the Milky Way dominates the sky, appearing as a defining feature of the universe. Yet, that same structure blocks our view of some of the most influential mass concentrations nearby. The glare that once symbolized our place in the cosmos also concealed forces shaping our motion through it. As Carl Sagan once noted in a different context, we are like butterflies who flutter for a day and think it is forever. The sentiment applies here not as philosophy, but as a practical observation about observational limits. Our vantage point inside the Milky Way shapes what we can see and how long it takes to uncover what lies beyond. Today, the Great Attractor is no longer entirely hidden, but it is still incomplete in our maps. Ongoing surveys continue to fill in missing regions, and future missions will refine mass estimates further. The glare of our galaxy remains a challenge, but no longer an insurmountable one. Astronomers gradually piece together what lies behind the Milky Way's disk. A broader picture began to take shape. What emerged? There was not an isolated structure, but part of a much larger gravitational landscape, with its pull extending toward even greater concentrations beyond the hidden region. Part 4. Is the Great Attractor a single monster object or a whole continent of galaxies? For many years, the Great Attractor was spoken of as if it were a single colossal thing, a hidden giant pulling the Milky Way and its neighbors toward one point in space. That image was powerful, but it was also misleading. As observations improved, astronomers began to see that there was no single object large enough, compact enough, to account for the motions they were measuring. What they were detecting was something broader, more distributed, and far more complex. The shift in understanding came gradually, not from one decisive observation, but from the accumulation of evidence across many surveys. As radio, infrared, and X-ray maps of the zone of avoidance became more complete, the region associated with the Great Attractor started to resolve into multiple dense structures rather than one dominant core. Each structure contributed to the gravitational pull, and together they formed a region of unusually high mass concentration. One of the most prominent components is the Norma cluster, also known as Abell 3627. Located at a distance of roughly 65 million light-years, it is among the most massive galaxy clusters in the nearby universe. X-ray observations from missions such as Rosat and Chandra revealed enormous amounts of hot gas trapped within its gravitational potential. The temperature and distribution of this gas indicate a deep well of dark matter, far outweighing the mass of visible galaxies. Yet the Norma cluster does not exist in isolation. Surrounding it is a larger network of clusters and galaxy groups forming part of the Hydra Centaurus region. This region extends over tens of megaparsecs and contains multiple dense nodes connected by filaments of galaxies. Optical surveys, where possible, combined with infrared and radio data, show that these structures are aligned along the same general direction indicated by large-scale galaxy flows. As astronomers began modeling the mass distribution of this area, a pattern emerged that challenged the idea of a single attractor. The gravitational influence could not be attributed to one cluster alone, not even one as massive as Norma. Instead, the combined mass of several clusters and surrounding dark matter halos produced a gravitational basin broad enough to shape the motion of galaxies across a vast region. This picture fits naturally within the framework of general relativity. In this context, gravity is not a force acting across empty space, but a response to how mass and energy shape the geometry of space-time. As John Wheeler expressed it, mass tells space-time how to curve, and space-time tells mass how to move. The Great Attractor region represents a place where that curvature is deeper than average, guiding the paths of galaxies nearby. The idea of a basin is not a metaphor meant to simplify, but a description grounded in calculations of gravitational potential. When astronomers reconstruct velocity fields from redshift surveys and distance measurements, they find streamlines converging into this region. The flows slow as they approach denser areas, much as predicted when matter moves through regions of increasing gravitational influence. These reconstructions rely on decades of work refining distance indicators. Techniques such as the Tully-Fisher relation for spiral galaxies and surface brightness fluctuations for ellipticals allowed astronomers to estimate distances independently of redshift. By comparing expected expansion velocities with observed velocities, they could infer where excess gravitational pull must be coming from. Repeatedly, the solutions pointed toward the same extended region. The Hydra Centaurus supercluster itself was recognized earlier, but its role within the Great Attractor picture became clearer only when its mass was placed in context. It contains numerous clusters, each contributing to the overall gravitational field. When their masses are added together, along with the dark matter that dominates each cluster, the result is a concentration large enough to explain the observed galaxy motions without invoking any exotic physics. What made this realization convincing was consistency. X-ray luminosities, galaxy velocity dispersions, and gravitational lensing estimates all pointed to similar mass values. Different observational methods, sensitive to different components of matter, converged on the same conclusion. The Great Attractor is not a single monster, but a crowded region where mass has accumulated over cosmic time. There is also a historical lesson embedded in this shift. Early descriptions favored simplicity, partly because data was sparse. A single attractor was easier to visualize and easier to communicate. As surveys expanded and computational tools improved, astronomers were forced to abandon that simplicity in favor of a more accurate, distributed picture. The change reflects how scientific understanding evolves with evidence. This distributed view aligns naturally with what is known about the cosmic web. Large-scale simulations of structure formation, supported by observations from NASA and ESA missions, show that matter in the universe is arranged in filaments, sheets, and nodes. Clusters form where filaments intersect, and superclusters emerge where many such intersections occur close together. The Great Attractor region fits this description precisely. Within this framework, the Norma cluster acts as a prominent node, but it is embedded in a larger structure that includes Hydra, Centaurus, and neighboring groups. Dark matter dominates the mass budget throughout this region, shaping the gravitational landscape in ways that visible galaxies alone cannot trace. This explains why early optical surveys underestimated the true scale of the attractor. Modern simulations, calibrated against observations, reproduce similar features. When initial density variations from the early universe are evolved forward under gravity, regions of enhanced density form naturally. These regions generate coherent flows of matter toward them, matching the patterns inferred from peculiar velocity surveys. The Great Attractor is one such feature, neither unique nor anomalous, but prominent because of its proximity. Understanding this also clarifies why the Great Attractor does not represent a final destination. Galaxies are not falling into a point from which there is no escape. They are moving through a landscape shaped by multiple overlapping mass concentrations, each influencing trajectories to varying degrees. The attractor is a local feature within a much larger network. As data accumulated, astronomers began to see that the flows toward the Great Attractor do not simply stop there. Beyond it, velocity reconstructions hint at additional influences from even larger structures. This raised an important question about how far the basin extends and whether it connects to deeper regions of mass concentration. The refinement of this picture owes much to patience. The Great Attractor was not resolved by sharper images alone, but by combining motion, mass estimates, and theory over decades. Each improvement reduced ambiguity, replacing speculation with measured structure. This methodical approach is characteristic of how astronomy advances when direct observation is difficult. Today, the Great Attractor is best described as a region, not an object. It is a convergence of clusters, groups, and dark matter halos, whose combined mass shapes the motion of galaxies nearby. This understanding preserves the observed phenomena while discarding the oversimplified image of a single hidden giant. Tracing the flow of galaxies across increasingly large scales revealed something unexpected beyond the Great Attractor itself. The emerging pattern suggested that this region may not represent the deepest gravitational basin influencing our motion. Part 5. Are we literally falling into the Great Attractor? And what would that future look like? The most direct way to understand our motion through the universe is not by watching nearby stars, but by comparing ourselves to the oldest light that still fills space. When astronomers measure the cosmic microwave background, they find that the local group of galaxies is moving with a clear, measurable velocity relative to that radiation. This motion is not subtle. It has a defined direction, a defined speed, and a consistency that has survived decades of increasingly precise observations. The cosmic microwave background acts as a reference frame because it originates from a time when the universe was hot, dense, and nearly uniform. Small temperature variations encode information about motion. One side of the sky appears slightly warmer, the opposite, slightly cooler. This pattern, known as the CMB dipole, indicates that the local group is moving at roughly 600 kilometers per second relative to this background. The direction of that motion aligns closely with the region associated with the Great Attractor. This alignment raises a careful question grounded in measurement rather than speculation. Are we falling toward the Great Attractor, or are we simply moving through a gravitational landscape shaped by multiple structures? To answer this, astronomers examine not just speed, but how velocity changes over time and across space. The local group includes the Milky Way, Andromeda, and dozens of smaller galaxies bound together by gravity. Within this group, motions are dominated by local interactions. The Milky Way and Andromeda are approaching each other at about 110 kilometers per second, a process expected to culminate in a merger several billion years from now. That local motion, however, is layered on top of a much larger scale movement involving thousands of galaxies. When astronomers subtract the effects of local gravitational interactions and the uniform expansion of space, a residual motion remains. This residual is coherent across many neighboring galaxy groups, not just our own. It points toward the same broad region, associated with the Great Attractor and the larger Laniakea supercluster. This coherence is what distinguishes a local orbit from a large-scale flow. The concept of Laniakea emerged in the early 2000s as astronomers refined velocity field reconstructions. Using distance measurements and redshift data, researchers traced how galaxies move relative to one another. They identified a vast region, spanning roughly 160 megaparsecs, where galaxy motions converge toward a common basin. This basin defines Laniakea, the supercluster that contains the Milky Way. Within this framework, the Great Attractor sits near the center of Laniakea's gravitational influence. Galaxies are not plunging straight inward as objects fall toward a compact mass. Instead, they follow curved trajectories shaped by the combined pull of clusters, filaments, and dark matter distributed throughout the region. The motion is gradual, measured over hundreds of millions of years, not sudden or catastrophic. To understand what this means for the future, astronomers turn to simulations. By evolving the current distribution of mass forward in time under the laws of gravity, they can estimate how galaxy positions will change. These models show that the Milky Way will continue to move within Laniakea's flow for a very long time, but it will not crash into a single central object. Instead, its trajectory will remain part of a broader circulation shaped by overlapping gravitational influences. One reason this motion does not lead to a dramatic endpoint is cosmic expansion. On the largest scales, space itself continues to expand, driven by dark energy. While gravity dominates locally and regionally, expansion becomes increasingly important at greater distances. This balance prevents superclusters like Laniakea from collapsing into single-bound objects. The Great Attractor exerts influence, but it does not override the expansion of the universe as a whole. Measurements from NASA and ESA missions support this picture. Observations of galaxy velocities show that while flows converge within Laniakea, they do not extend indefinitely. Beyond certain scales, galaxies participate more strongly in the overall expansion, reducing the net effect of any single attractor. This explains why the Great Attractor shapes regional motion without dictating the fate of the entire universe. Over hundreds of millions of years, the sky, as seen from Earth, will change subtly. Nearby galaxies will shift positions. The large-scale pattern of galaxy distribution will evolve. But these changes unfold on timescales far longer than human history. The stars of the Milky Way will continue their own orbits, largely unaffected by the galaxy's slow translation through space. The history behind these conclusions reflects caution rather than drama. Early interpretations of the Great Attractor sometimes implied an inevitable plunge toward a hidden mass. As data improved, that language softened. Astronomers replaced the idea of falling with the concept of flowing. The distinction matters because it reflects how gravity operates on large scales. Flow implies direction without a singular destination. It reflects the gradient of mass density rather than the presence of a single endpoint. In this sense, the local group is participating in a long-term migration within a structured environment, not a one-way descent. This view aligns with both observation and theory. The cosmic microwave background continues to serve as a crucial anchor in these studies. By providing a reference frame independent of local structures, it allows astronomers to measure absolute motion rather than relative drift. Each new dataset refines the velocity of the local group, narrowing uncertainties and confirming the same overall picture. Future missions will sharpen this understanding further. ESA's Euclid mission and next-generation radio surveys aim to map dark matter distribution with greater precision. These observations will improve models of gravitational flow within Laniakea and clarify how the Great Attractor fits into the broader cosmic web. They will not overturn the basic conclusion, but they will add detail and confidence. The question of whether we are falling into the Great Attractor ultimately resolves into a matter of scale and language. On small scales, galaxies fall toward clusters. On larger scales, they move along paths defined by many overlapping influences. The local group's motion reflects the latter. It is shaped by the Great Attractor, but not destined for a final collision. This understanding reframes the future of the Milky Way. Its most dramatic events lie closer to home, such as the eventual merger with Andromeda. The motion toward the Great Attractor will continue quietly in the background, a steady translation rather than a defining event. The structure of Laniakea provides context, not a deadline. As astronomers extended their maps beyond Laniakea, another pattern began to appear. The flow lines do not end at the Great Attractor. They continue outward, hinting at even larger mass concentrations influencing motion on still greater scales. This realization does not diminish the importance of the Great Attractor. It places it within a hierarchy of structure. The data place the Great Attractor within a wider gravitational setting. What appears to us as a dominant pull may itself be only one layer of a deeper gravitational landscape, extending well beyond our immediate cosmic neighborhood. Part 6. How much of this pull comes from dark matter we can never see directly? The most uncomfortable realization about the Great Attractor is that most of the mass doing the pulling does not shine, does not glow, and does not announce itself in any familiar way. When astronomers add up all the stars, gas, and dust visible in the region, the numbers fall far short of what is required to explain the observed motions of galaxies. Something else must be present, something far more abundant than ordinary matter, quietly shaping the gravitational landscape. This conclusion did not arise from speculation. It emerged from repeated failures of visible matter to account for motion. Long before the Great Attractor was discussed, astronomers studying galaxy rotation curves noticed a similar problem. Stars in spiral galaxies orbit too fast to be held together by the gravity of visible matter alone. The same discrepancy appears on much larger scales, including clusters and superclusters. By the late 20th century, this invisible component had a name: dark matter. Not because it is mysterious by choice, but because it does not emit or absorb electromagnetic radiation. Telescopes cannot image it directly. Its presence is inferred entirely through gravity. In the region associated with the Great Attractor, dark matter dominates the mass budget. Measurements of galaxy velocities and cluster dynamics indicate that for every unit of mass in stars and gas, there are several units of mass in dark matter. In many clusters, the ratio approaches 5:1. This imbalance means that most of the gravitational pull shaping galaxy motion comes from matter we cannot see. The idea of dark matter halos provides a useful framework. Galaxies are not isolated islands of stars. They are embedded in extended halos of dark matter that stretch far beyond their visible edges. These halos overlap and merge within clusters and along filaments of the cosmic web, creating continuous regions of enhanced mass density. The Great Attractor region sits at a junction of such structures. Evidence for these halos comes from multiple directions. One of the most direct is gravitational lensing. According to general relativity, mass bends the path of light. When light from distant galaxies passes near massive foreground structures, its path is deflected, distorting the images we observe. These distortions allow astronomers to map mass directly, regardless of whether it emits light. Observations from NASA's Hubble Space Telescope and ESA missions have used weak gravitational lensing to reconstruct mass distributions in clusters near the Great Attractor. The resulting maps consistently show that most of the mass does not coincide with visible galaxies. Instead, it forms broad halos and filaments that extend well beyond the luminous components. X-ray observations reinforce this picture. Hot gas trapped in clusters emits X-rays, and its temperature reflects the depth of the gravitational potential well. In regions like the Norma cluster, the gas temperature indicates a total mass far exceeding what stars alone could provide. Dark matter accounts for the difference. Radio and infrared surveys add further support. They reveal galaxies hidden by dust, increasing estimates of visible matter, but not nearly enough to close the gap. Even after accounting for every detectable galaxy, the gravitational pull remains too strong. The conclusion persists across wavelengths. The cosmic web provides the larger context. On the largest scales, matter in the universe is arranged in filaments, sheets, and nodes. Dark matter forms the scaffolding of this web. Ordinary matter falls into these structures, forming galaxies and clusters along the underlying dark matter distribution. The Great Attractor is part of this network, not an isolated anomaly. Simulations play a crucial role in understanding this process. Using initial conditions measured from the cosmic microwave background, researchers evolve the universe forward in time under gravity. These simulations consistently produce regions of enhanced mass connected by filaments, with coherent flows of matter toward dense nodes. The patterns closely resemble those inferred from galaxy velocity surveys around the Great Attractor. NASA has emphasized that dark matter is essential for explaining these structures. Without it, galaxies would not form as early as they do, and large-scale flows would be far weaker than observed. The motions toward the Great Attractor fit naturally into this framework. The role of dark matter becomes even clearer when examining peculiar velocities. These deviations from uniform expansion trace gravitational gradients. When astronomers model these velocities using only visible matter, the predicted flows fall short. When dark matter is included, the models align with observations. This consistency has been demonstrated repeatedly in independent studies. One illustrative example comes from studies of cluster mergers. When clusters collide, the hot gas can be stripped and displaced, while dark matter halos pass through with minimal interaction. Gravitational lensing reveals where the mass actually resides, and it often does not coincide with the brightest regions. These events provide direct evidence that most mass is invisible and collisionless. Although the Great Attractor itself has not been observed in such a dramatic merger, the same principles apply. The mass-shaping galaxy motion there is distributed broadly, dominated by dark matter halos, overlapping across clusters and filaments. The visible galaxies trace only the peaks of this distribution. Understanding how much of the pull comes from dark matter also clarifies why the Great Attractor was difficult to identify initially. Optical surveys map light, not mass. If most of the mass lies in dark halos, optical maps will underestimate the true gravitational influence. The mismatch between motion and light was the clue. ESA's Planck mission provided further confirmation by measuring the distribution of matter through its effects on the cosmic microwave background. Subtle distortions in the background radiation reveal how mass is distributed along the line of sight. These measurements are consistent with a universe dominated by dark matter, including in regions associated with large-scale flows. The dark matter component also explains why the Great Attractor does not appear as a single compact object. Dark matter spreads out, forming extended halos rather than dense cores like stars. The resulting gravitational influence is broad and gradual, shaping motion over large distances rather than producing sharp accelerations. This matches what is observed. The story of dark matter is also a story of restraint. Astronomers did not accept its existence lightly. Decades of alternative explanations were tested and rejected as data accumulated. Modified gravity theories, observational biases, and measurement errors were examined carefully. The persistence of the discrepancy across scales and methods left little room for doubt. Today, dark matter remains unidentified at the particle level, but its gravitational effects are firmly established. For the Great Attractor, this means that most of the pull guiding galaxy motion originates from matter that cannot be imaged directly. The conclusion is not dramatic. It is simply what the measurements require. This understanding reshapes how astronomers describe the region. The Great Attractor is not a luminous beacon hidden behind dust. It is a dense intersection of dark matter filaments, marked by clusters like Norma and Hydra, Centaurus, with visible galaxies acting as tracers rather than drivers. The true structure lies beneath the light. Future observations aim to refine this picture, Surveys designed to map weak gravitational lensing across large areas of sky will improve mass reconstructions. Combined with deeper redshift surveys, they will sharpen estimates of how dark matter is distributed within Laniakea and beyond. These efforts will not overturn the role of dark matter, but they will define it more precisely. The question of how much of the pull comes from dark matter, therefore, has a clear answer grounded in evidence. Most of it does. The stars and gas are passengers within a much larger mass distribution, one that shapes motion silently and persistently. Extending mass maps to larger distances revealed a continued structure beyond the Great Attractor. The dark matter concentrations influencing its motion did not stop there, but linked outward to even larger assemblies farther away. Part 7. Is the Great Attractor only a foreground ripple of an even deeper Shapley attractor? The moment astronomers extended their maps beyond the region of the Great Attractor, the story changed in a way that could not be ignored. The galaxy flows did not slow down, and they did not terminate at the mass concentration we had been tracking for decades. Instead, the velocity field continued onward, pointing towards something larger, more distant, and far more massive than the Great Attractor itself. This realization did not come from a single observation. It emerged as flow maps grew in scale and precision. When astronomers reconstructed galaxy motions across hundreds of millions of light-years, they began to notice that the Great Attractor behaved less like a final destination and more like an intermediate feature. Galaxies appeared to pass through its region of influence, continuing along paths shaped by an even deeper gravitational landscape. The structure that stood out in these extended maps was the Shapley supercluster. Located roughly 200 to 300 megaparsecs away, the Shapley supercluster is one of the most massive concentrations of galaxies known in the nearby universe. It contains dozens of rich galaxy clusters, each with enormous dark matter halos, forming a structure whose total mass rivals or exceeds that of many other superclusters combined. Historically, the Shapley supercluster was known as a remarkable overdensity, but its dynamical role was not immediately clear. Early redshift surveys revealed its richness, but distance uncertainties made it difficult to assess its influence on galaxy motion. As measurement techniques improved, particularly through large-scale velocity surveys, the picture sharpened. One of the key developments was the refinement of cosmic flow maps. By combining galaxy distances with redshift data, astronomers could isolate peculiar velocities and reconstruct how galaxies move relative to the expanding universe. When these maps extended far enough, they revealed a striking continuity. The same flow lines that converged near the Great Attractor continued onward toward the Shapley region. This continuity forced a re-evaluation of earlier assumptions. If the Great Attractor were the dominant mass concentration shaping local motion, flows should slow and disperse beyond it. They did not. Instead, the velocity vectors remained aligned, suggesting that the Great Attractor sits along a gradient leading toward a more massive structure farther away. The Shapley supercluster fits this requirement. Its estimated mass, derived from cluster dynamics, X-ray observations, and gravitational lensing, is immense. The hot intracluster gas, detected by X-ray telescopes such as Rosat and Chandra, indicates deep gravitational potentials across the region. These measurements imply a concentration of dark matter far exceeding that of individual clusters like Norma. Simulations of large-scale structure formation provide essential context. When initial density fluctuations from the cosmic microwave background are evolved forward under gravity, the resulting universe naturally forms hierarchical structures. Smaller attractors emerge first, embedded within larger basins that dominate on greater scales. In this framework, the Great Attractor appears as a local feature within a much broader gravitational descent toward Shapley. NASA and ESA have emphasized that galaxy flows reflect this hierarchy. Galaxies respond most strongly to nearby mass concentrations, but their overall trajectories are shaped by cumulative influences extending far beyond local neighborhoods. The Shapley supercluster represents one of the deepest such influences within the observable universe accessible to current surveys. The distinction between local and large-scale influence becomes clear when examining velocity amplitudes. The Great Attractor accounts for a significant portion of the local group's motion, but not all of it. When Shapley's mass is included in models, the remaining discrepancy largely disappears. The combined gravitational pull aligns closely with the observed motion relative to the cosmic microwave background. This does not mean that galaxies are falling directly into Shapley as isolated objects. As with the Great Attractor, the motion is gradual and distributed. Galaxies move along filaments of the cosmic web, guided by overlapping gravitational gradients rather than plunging toward a single point. The influence of Shapley is felt across an enormous volume, shaping flows without imposing a sharp boundary. There is an important observational story behind this conclusion. Early studies hesitated to attribute too much influence to Shapley because of its distance. At hundreds of megaparsecs, uncertainties in distance measurements grow, and the risk of systematic error increases. Astronomers responded by expanding datasets, cross-checking independent surveys, and refining statistical methods. The persistence of the Shapley signal across these efforts strengthened confidence. Infrared and radio surveys played a crucial role once again. By penetrating dust and extending coverage across the sky, they reduced biases that might distort flow reconstructions. The inclusion of these data made the continuity of flows towards Shapley more difficult to dismiss as coincidence. The Shapley supercluster also stands out in sheer richness. It contains some of the most massive clusters known, with galaxy densities far above the cosmic average. Each of these clusters contributes to the total gravitational field, and together they form a region capable of influencing galaxy motion over hundreds of millions of light years. In terms of mass concentration, Shapley represents an extreme, but not an anomaly. This realization reframes the role of the Great Attractor. Rather than acting as the ultimate cause of our motion, it appears as a foreground feature, a dense step along a larger gravitational slope. Its influence is real and measurable, but it does not exist in isolation. It is embedded within a larger structure whose pull extends farther and deeper. The language used by astronomers reflects this shift. The term Shapley Attractor has been used cautiously, not to replace the Great Attractor, but to describe the deeper basin shaping regional flows. This terminology emphasizes continuity rather than competition between structures. Both attractors are part of the same gravitational landscape. The broader implication is that motion in the universe is scale-dependent. On small scales, galaxies orbit within groups. On intermediate scales, they move within superclusters like Laniakea. On larger scales still, structures like Shapley influence entire regions of the observable universe. Each level builds upon the last. This layered picture aligns closely with what is seen in numerical simulations and observational surveys. It requires no new physics, only careful accounting of mass across scales. Dark matter plays a central role, amplifying the influence of large structures and extending their reach. Without it, the observed coherence of galaxy flows would be impossible. The story of Shapley's role also underscores how astronomy advances. It is not driven by dramatic revelations, but by gradual extensions of perspective. Each new survey pushes the horizon outward, revealing that what once seemed dominant is part of something larger. The Great Attractor was not diminished by this process. It was contextualized. Today, the Shapley supercluster stands as one of the strongest known influences on galaxy motion in our cosmic neighborhood. Its gravitational reach likely shapes the motion of not just the Milky Way, but thousands of galaxy groups spread across vast distances. The Great Attractor marks where this influence becomes locally apparent. Continued mapping has pushed attention beyond the Shapley region itself. If Shapley marks a deeper gravitational basin, the data allow for influences extending even farther outward, approaching the limits of what can be observed directly. Flow maps already show subtle irregularities in galaxy motion that current models do not fully account for. Part 8. What did the Laniakea map reveal about the river of galaxies carrying us along? The unsettling detail was not that galaxies were moving, but that they were moving together. When astronomers finally assembled velocity data across a wide enough region of space, the Milky Way no longer appeared as an isolated traveler. It was embedded in a coherent pattern of motion, shared by thousands of galaxies, all drifting along paths that pointed in the same general direction. This realization reached clarity in the early 2000s, when Brent Tully and his collaborators began reconstructing galaxy velocity fields using increasingly precise distance measurements. Rather than focusing on where galaxies were located, they focused on how they were moving, separating the smooth expansion of the universe from the additional motions imposed by gravity. The result was not a scatter of random arrows, but a structured flow. The method was careful and conservative. Distances were estimated using multiple independent techniques, including the Tully-Fisher relation and surface brightness fluctuations. Redshifts provided velocities, while corrections removed the effects of local interactions and cosmic expansion. What remained was the residual motion, the part driven purely by gravitational imbalance. When these residuals were plotted in 3 dimensions, a striking pattern emerged. Galaxies traced long, continuous paths. These paths converged into regions of higher mass density and diverged away from voids. The motions resembled currents shaped by an uneven gravitational landscape. This was not a metaphor invented for convenience. It was a direct visualization of how matter responds to gravity on the largest scales we can measure. From these reconstructions, the concept of Laniakea took shape. Laniakea is not a cluster, not a supercluster in the traditional sense, and not a bound object. It is a basin of attraction, a region of space defined by the way galaxies move rather than how they appear. Within its boundaries, galaxy motions converge toward a common gravitational low point. Outside those boundaries, flows turn elsewhere. The Milky Way lies firmly inside this basin. So do Andromeda, the Virgo cluster, and thousands of other galaxies spread across roughly 160 megaparsecs. This scale was not chosen arbitrarily. It emerged naturally from the velocity field itself. Where flow lines diverged, the edge of Laniakea was drawn. The map was defined by motion, not brightness. What made this result compelling was its independence from any single dataset. Different surveys, using different telescopes and distance indicators, produced compatible flow patterns. The boundaries of Laniakea shifted slightly with improved data, but the overall structure remained stable. This consistency gave astronomers confidence that they were seeing a real feature of the universe. The idea of a basin of attraction comes directly from gravitational physics. Where mass density is higher, space-time curves more strongly. Galaxies respond by adjusting their trajectories, accelerating gently toward regions of deeper curvature. Over vast distances, these small accelerations accumulate into coherent motion. Laniakea represents one such region where mass concentration dominates the surrounding gravitational field. The Great Attractor sits near the center of this basin. It is not the only mass concentration within Laniakea, but it marks a significant low point in the gravitational landscape. The velocity field shows galaxies flowing toward it from many directions, including our own local group. This clarified the role of the Great Attractor as a central feature within a larger structure. The story behind this mapping effort reflects a shift in how astronomers think about cosmic structure. Earlier models defined superclusters by counting galaxies or measuring luminosity. The Laniakea map defined structure by motion. It asked a different question, not where galaxies are, but where they are going. That change in perspective revealed connections that brightness alone could not. NASA and ESA data played a supporting role in refining this picture. Observations of the cosmic microwave background provided an absolute reference frame, ensuring that velocities were measured consistently across the sky. Infrared and radio surveys filled gaps caused by dust obscuration, especially near the zone of avoidance. Each contribution reduced uncertainty and sharpened the flow map. The resulting visualization showed that galaxy motion is not chaotic. On the largest scales, it is highly organized. Galaxies follow paths defined by the distribution of dark matter, which forms the underlying framework of the cosmic web. Laniakea is one basin within that web, carved by the accumulated mass of clusters, groups, and filaments. Importantly, Laniakea is not gravitationally bound in the way a galaxy cluster is. Dark energy and cosmic expansion prevent the entire region from collapsing into a single object. Galaxies within Laniakea are influenced by its gravitational gradient, but they are not destined to merge at its center. The basin defines motion, not fate. This distinction resolved confusion surrounding earlier descriptions of the Great Attractor. Rather than imagining galaxies falling into a hidden monster, astronomers could now describe a smoother, more distributed process. Galaxies move along gradients shaped by many overlapping mass concentrations. The Great Attractor is a prominent feature within that flow, not its ultimate endpoint. The velocity field also revealed the presence of neighboring basins. Just beyond the boundaries of Laniakea, flow lines bend toward other mass concentrations, including the Shapley supercluster. This confirmed that Laniakea is one region within a larger hierarchy. Its influence is substantial, but not universal. One of the most valuable aspects of the Laniakea map was what it did not assume. It did not rely on models of galaxy formation or assumptions about how mass should be distributed. It relied on motion alone. If galaxies moved in a certain way, the mass causing that motion had to exist, whether visible or not. This made the result robust. The emotional impact of the discovery was quiet, but lasting. For the first time, astronomers could place the Milky Way within a clearly defined large-scale flow. Our galaxy was no longer just part of a vague local supercluster. It had an address within a dynamic structure shaped by gravity. The map provided context rather than drama. Carl Sagan often emphasized that understanding comes from placing ourselves within a larger framework. In discussing cosmic structure, he once noted that maps change how we understand our position, not by shrinking us, but by locating us accurately. The Laniakea map accomplished exactly that, using motion as its guide. As datasets continue to grow, the boundaries of Laniakea will be refined. New distance measurements, improved velocity reconstructions, and deeper surveys will adjust details. But the core result is unlikely to change. Galaxies move in organized flows, and the Milky Way is part of one such flow within Laniakea. The river is real because gravity demands it. The Laniakea map did more than define a structure, it demonstrated a method. By following motion rather than light, astronomers uncovered a hidden order shaping the universe on the largest scales accessible to observation. That method now points outward once again, beyond Laniakea, toward regions where flows behave less predictably. At the edge of these maps, subtle anomalies remain. Some motions appear too large to be explained by known structures alone. These hints suggest influences extending beyond the boundaries we can currently chart. That unresolved tension carries us forward into Part 9. Could there be even larger hidden attractors beyond the edge of what we can observe? The most unsettling possibility raised by modern cosmology is not that we are being pulled by something unseen, but that the pull may not stop where our maps end. When astronomers extend their measurements of galaxy motion to the largest scales accessible to observation, some patterns remain that cannot be fully explained by known structures such as the Great Attractor, Laniakea, or even the Shapley supercluster. These residual motions appear as large-scale bulk flows, subtle but persistent, stretching across hundreds of millions of light years. To understand why this is remarkable, it helps to recall what defines the limit of what we can observe. The cosmic horizon is not a physical wall in space. It is a boundary set by time and the finite speed of light. Beyond this horizon, light has not had enough time since the beginning of cosmic expansion to reach us. Any structure lying beyond it is, by definition, unobservable directly. Yet gravity, unlike light, is not blocked by distance in the same way. Astronomers became aware of this tension while studying bulk flows, coherent motions of galaxy groups extending over vast regions. These flows are measured by comparing galaxy velocities to the reference frame provided by the cosmic microwave background. When the velocities of thousands of galaxies are averaged over large volumes, a net motion sometimes remains. In several surveys, this motion appeared larger than expected from known mass distributions alone. Early discussions of bulk flow measurements were cautious. Distance uncertainties grow with scale, and systematic errors can masquerade as coherent motion. Astronomers responded by refining methods, combining independent datasets, and testing for biases. Some early claims of extreme flows were softened as data improved. But even with conservative analysis, certain anisotropies persisted. One source of insight came from the cosmic microwave background itself. Its temperature fluctuations encode information about density variations in the early universe. Large angle anomalies and dipole alignments have been studied extensively by NASA's COBE mission, WMAP, and ESA's Planck satellite. While the standard cosmological model explains most features remarkably well, a small number of large-scale patterns remain topics of active investigation. These patterns raised a natural question grounded in physics rather than speculation. If mass distributions beyond our observable horizon exist, could their combined gravitational influence subtly affect motions within the observable universe? General relativity allows for this possibility. Gravity responds to mass energy, regardless of whether that mass can be seen directly. Theoretical work provides context for this idea. Inflationary cosmology predicts that the universe on scales larger than our observable region could be far more extensive and structured than what we can detect. Alan Guth, one of the pioneers of inflation theory, summarized this perspective succinctly. There may be an enormous amount of universe beyond the part we can observe. This statement is not a claim of hidden attractors, but a reminder of scale. Within this framework, superhorizon structures are not exotic additions. They are a natural consequence of a universe larger than our observable patch. Density variations on scales beyond the horizon would not be directly visible, but their gravitational effects could influence the motion of matter within the horizon, especially over long timescales. Astronomers have explored this possibility through simulations. By modeling universes with slightly different large-scale density distributions, researchers can examine how bulk flows respond. In some scenarios, long wavelength density gradients produce coherent motions resembling those observed. These models do not require new physics, only variations in initial conditions. Observationally, the challenge is separating local effects from truly superhorizon influences. Known structures such as Shapley exert significant pull and must be accounted for precisely. When these contributions are subtracted, any remaining flow becomes the signal of interest. This process is delicate and subject to debate. Data from galaxy surveys, including those supported by NASA and ESA, show that most observed flows can be explained by known large-scale structure within the observable universe. However, the margins are not zero. Some analyses report residual motions at levels that invite further scrutiny. These findings are not definitive evidence, but they are not dismissed outright. The study of anisotropy provides another angle. The universe appears remarkably uniform on large scales, yet small directional differences exist. These differences are measured in galaxy distributions, velocity fields, and the cosmic microwave background. While most align with expectations from cosmic variance, a few correlations remain unexplained. Importantly, astronomers resist framing these anomalies as proof of hidden attractors. The history of cosmology is filled with apparent discrepancies that vanished with better data. Improved calibration, deeper surveys, and refined statistical methods often resolve tensions without invoking unseen structures. Caution is not skepticism, but discipline. At the same time, the possibility itself reshapes perspective. The Great Attractor and Shapley supercluster taught astronomers that unseen mass can dominate motion on scales once thought well understood. It is therefore reasonable to ask whether even larger scales might hold additional surprises. The question is not whether they exist, but whether their influence is measurable. Future missions will help address this. ESA's Euclid mission and upcoming radio surveys aim to map galaxy distributions and weak gravitational lensing across unprecedented volumes. These observations will improve constraints on bulk flows and test whether residual motions persist as data quality improves. JWST, while focused on deep field observations, contributes indirectly by refining models of structure formation. If residual flows remain after these efforts, the implications would be profound but not destabilizing. They would suggest that our observable universe is responding to conditions set on even larger scales. This would align naturally with inflationary predictions, reinforcing rather than challenging the standard model. If the anomalies fade, the lesson will be equally valuable. It will confirm that known structures account for observed motion and that earlier hints were artifacts of limited data. In either case, The process advances understanding through restraint and evidence. The idea of unseen attractors beyond the cosmic horizon should therefore be held with balance. It is neither a speculative fantasy nor an established fact. It is a question that emerges from precise measurement and remains open because the universe is large and our observations are finite. Carl Sagan often emphasized that science is a way of asking questions that can be answered, or at least constrained, by evidence. In discussing cosmic horizons, he noted that the observable universe is not the same as the entire universe, a distinction grounded in physics rather than imagination. That distinction frames the discussion here. The Great Attractor began as an anomaly in galaxy motion. It became a well-defined feature once enough data were gathered. The Shapley supercluster extended that picture further. Now, the edge of observation presents another boundary where motion meets uncertainty. Whether that boundary hides deeper attractors or simply reflects the limits of measurement remains to be seen. What is clear is that galaxy motion continues to be one of the most sensitive probes of mass distribution. Light tells us where stars are. Motion tells us where gravity comes from. When the two disagree, astronomy listens carefully. As maps of motion reach their limits, interpretation becomes cautious and methodical. Astronomers do not rush to fill gaps with speculation. They wait for new data, refine models, and test alternatives. This patience is what transformed the Great Attractor from rumor into structure. The possibility of even larger hidden influences therefore stands not as a claim, but as a boundary marker. It shows where current knowledge ends and where future observation must begin. It is an invitation to improve measurement rather than to accept mystery. As this exploration reaches the edge of what we can observe, the final step is not outward, but inward. Having traced motion from local clusters to superclusters and possibly beyond the horizon, the remaining task is to ask what this entire chain of influence reveals about the universe as a whole. That perspective draws us toward the final synthesis in Part 10. What does being pulled by the Great Attractor tell us about the true shape of the universe? The most decisive evidence that the universe is not a static backdrop comes from motion itself. When astronomers measure how galaxies move, they find patterns that cannot be explained by chance alignment or isolated interactions. The Milky Way's path, traced through redshift surveys, cosmic microwave background measurements, and velocity field reconstructions, shows that our galaxy is embedded within a structured network of mass that shapes motion across immense distances. This understanding did not emerge from a single experiment. It emerged from the convergence of many independent observations. The cosmic microwave background provides a reference frame against which motion can be measured with precision. Large galaxy surveys reveal how velocities deviate from uniform expansion. Weak gravitational lensing maps the distribution of mass regardless of whether it emits light. Together, these tools show that galaxy motion reflects the geometry of mass in the universe. The Great Attractor plays a central role in this picture, not because it is unique, but because it is nearby enough to be measured in detail. It demonstrated clearly that visible matter alone does not define structure. The gravitational pull guiding our motion arises from the combined mass of clusters, filaments, and dark matter halos arranged within a larger framework. This framework is what astronomers now describe as the cosmic web. In this web, matter is not distributed evenly. Dense regions form nodes where clusters gather. Filaments connect these nodes across tens and hundreds of megaparsecs. Vast voids separate them. Galaxies move along this network, responding to gradients in mass density rather than orbiting a single center. The Great Attractor marks a significant node within this system. Understanding motion in this way changes how astronomers describe the shape of the universe on large scales. Geometry here does not mean curvature in the everyday sense, but the arrangement of mass that determines how space-time guides motion. Where mass is concentrated, trajectories bend. Where mass thins, motion accelerates away. The resulting paths form coherent flows that can be mapped and tested against observation. This perspective aligns closely with predictions from general relativity and cosmological simulations. When initial density variations measured in the cosmic microwave background are evolved forward under gravity, the resulting universe develops structures remarkably similar to those observed. Clusters form at filament intersections. Superclusters emerge as extended regions of influence. Galaxy flows trace these features naturally. NASA and ESA missions have played a crucial role in validating this view. Measurements from COBE, WMAP, and Planck established the reference frame for motion. Large optical, infrared, and radio surveys filled in the distribution of galaxies. Weak lensing studies provided direct mass maps. Each dataset reinforced the same conclusion: motion follows mass. The Great Attractor also clarified the role of dark matter in shaping cosmic geometry. Without dark matter, the observed flows would be far weaker and less coherent. Visible galaxies alone cannot account for the depth or extent of the gravitational basins that guide motion. Dark matter provides the dominant contribution, forming the unseen structure within which luminous matter resides. This realization resolved earlier confusion about whether galaxies were falling into isolated objects. They are not. They are moving through a continuous landscape shaped by overlapping influences. The language of basins and flows reflects measured behavior, not metaphor. It describes how gravity operates across scales where no single object dominates. The Laniakea map made this especially clear. By defining structure through velocity rather than brightness, it showed that superclusters are best understood as regions of coordinated motion. Boundaries are drawn where flow lines diverge, not where galaxy counts abruptly change. This approach reveals the dynamic shape of the universe rather than a static snapshot. Seen from this perspective, the Milky Way's motion is not unusual. It is typical of galaxies embedded in the cosmic web. Our solar system, our star, and our planet are carried along within this larger flow without any local disturbance. The motion is smooth, gradual, and measured over hundreds of millions of years. The broader implication is that the universe has a kind of large-scale organization that can be inferred from motion alone. This organization does not imply purpose or direction. It reflects the outcome of gravity acting on an initially uneven distribution of matter over cosmic time. The shape we observe is the shape gravity produces. The Great Attractor also served as a reminder of observational humility. For many years, it was hidden behind the Milky Way's disk. Its influence was detected before its structure was seen. Motion revealed what light concealed. This lesson applies broadly in cosmology, where indirect evidence often leads discovery. Carl Sagan often emphasized that science advances by connecting evidence across scales. In discussing cosmic structure, he noted that our location gains meaning only when placed within a larger context supported by data. The story of the Great Attractor exemplifies this approach. It links local motion to superclusters, and superclusters to the geometry of the universe. As surveys continue to expand, the details of this picture will sharpen, boundaries will be refined, mass estimates will improve, velocity fields will extend farther. But the underlying conclusion is unlikely to change. The universe is structured. Motion is organized. Gravity connects regions across vast distances. The question posed at the beginning of this journey now has a measured answer. Being pulled by the Great Attractor tells us that our galaxy's path is not random. It is shaped by a network of mass that spans hundreds of millions of light years. This network defines basins and flows that guide motion without requiring a central anchor. The universe is not a featureless stage. It is an interconnected system. The significance of this insight lies not in scale alone, but in method. By listening to motion, astronomers inferred structure. By comparing independent observations, they tested and refined that inference. The result is a view of the universe grounded in measurement rather than assumption. This perspective also places limits on speculation. While structures may exist beyond what we can observe, the motions we measure within the observable universe are largely accounted for by known mass distributions. The Great Attractor and its larger context fit naturally within established physics. Mystery remains, but it is bounded by evidence. As this exploration comes to rest, the picture that remains is clear and steady. Our galaxy moves as part of a larger flow. That flow traces the shape of mass in the universe. The Great Attractor is one feature within a vast, connected structure that continues beyond our immediate view. The universe reveals its shape through motion. Thank you for spending this time following the evidence step by step. If you are listening as the day ends or the night settles in, may the steady pace of these motions carry your thoughts toward rest. The universe continues its measured flow, and so can you. Good night.